So we're going to do that here. df.index equals to range 7. That's what we have done. And we're going to do something that is a little bit advanced here. Now we have covered lambda, right, in our functions and lambdas discussion. And basically this is using, I'm going to extract the first 2 rows. Okay, let's just put the dot apply map next in the next line so you can see. So what the first line does is basically quite easy to understand. We want the first 2 rows inclusive. Remember, this is dot log. We are going to refer to the rows by labels, and we do mean to include the end label 1 here across all columns. So it will be essentially extracting these 2. And what the second part does is to apply map. Apply map just means that apply this function to all the cells in this 2 by 10 data frame data. Now, our apply map here is very similar to apply function to all elements in the list discussion that we had in the videos for functions and lambdas. When we talked about lambdas that time, I illustrated an example of how we can use a lambda to transform the data items in the list. Because at that time, we haven't talked about pandas, right? So it's not easy to talk about that here. But now that we understand what is pandas and data frames, we can actually quite easily understand this dot apply map, except it is spelled as dot apply map. But essentially, it's doing the same thing. It takes a function that we say, which is this lambda x here, and apply the transformation. What is that transformation? It's going to change the x to 2 decimal places, because right now there are how many? 6 decimal places, or maybe even more, because this is just a printout. And it's just too massive, right? So we like to kind of truncate it to 2 decimal places. How can we do that? Yeah. So we are going to do 2 things. We're going to change it to 2 decimal places, and now changing it into a string. So rather than a float, the outcome will be a string. And we're going to apply this transformation to each and every cell. And that's what apply map is for. Each and every cell in this 2 by 10 new data frame. And this is called DFA. Let's try and run it and see. Okay, I hope you see the same thing as I do, right? Because although it's based on random numbers, all our random numbers are the same. So when we subject those random numbers to the same treatment and transformation, all of us should see the same outcome. Now, here, all these are not just floating points, because we also changed it to string using the f-string format. We could have just used round, NP round, numpy's rounding to round it so that we maintain the float. But sometimes float, when you round to 2 decimal places, you still get back 0.4699999, something like that. So the only frozen way to lock it down to 2 decimal places is to use string. So here, let's just go along with me for a while. So my DFA is this very neat string that is probably reminiscent of our earlier discussion for this slide here, right? And that's exactly where I'm heading. Okay, so you should see elements of this negative 0.83, negative 1.1 coming out somewhere here, right? Now we like to pick out these cells. Yeah, okay. And what we're going to do is, well, I'm just going to copy and paste from the slide, and first define short names. So I don't have to, but it just makes the the data frame mask easier to define. So when I have T for true and F for false, I can easily create a list. So this list of true false, right, is actually what is happening here. So we can explicitly type it in here like this, or we can just replace it with the list underscore true false. Let's just do that one at a time. So for now, we don't have to uh, do it. We can leave it there. And we use this dfa underscore true false. So remember, this shape 2 by 10 has to be exactly the same as dfa. Otherwise, it won't work because you're mismatching the size. So they have to be exact size and they have to be true or false. Right? Then the columns need to match. The columns need to match. All right. And that's to ensure that we are actually applying the right true false to the right column. Then the magic happens when you say DFA square bracket DFA. All right, where we have an underscore true false to indicate the mask. Now we print out what is DFB, which should be exactly what we have discussed. So the first version is the DFA, and the second version is pulling out exactly those locations where we have put a true to it. Yeah, okay. So in essence, uh, this complicated looking thing is just list underscore tf. That's all. That's all there. Okay. So it's exactly going to produce the same outcome. Okay. And what if we don't supply just to make it more compact? Can we not do that? You'll find that it's a little bit risky not to have the same column because the columns are saying what is to be matched with what. So if we look at DFA underscore TF, it's trying to say that for column labeled with 0, I want a false false. For column labeled with 1, I want a true false. The first one I want, second one I don't want, and so on. And when you put into a selector filter like this, DFA underscore TF, and where DFA underscore TF doesn't have the same column names as DFA, the pandas selector is going to look at column label and say 0 I match with, I cannot see any 0, so discard. 1 match with, I don't see whatever I can select, so discard, and so on. So whatever the selector wants, the mask wants, you don't have, right? You don't have a 0, 1, 2, 3 label. So end up, what's the outcome? It will be an outcome that is the same as the original data frame, but which nothing has been selected. So it is therefore correct that we see a NaN and so on. Okay. Now, what happens if we restore the column partially? Okay. So if we do that, then what happens? Well, then first 5 columns will match, and we get to do what we want for the first 5 columns. The last 5 columns are basically A, B, C, D, E trying to match with 0, 1, 2, 3, 4, and nothing matches, so nothing is selected. I hope now it makes sense, right? So when you twiddle around with the true false and play around with the columns, sometimes not knowing that the columns must match, again, creates a lot of frustration. Okay, fortunately, the sort of problems end here, and we are able to just uh, get by it without having to worry about other stuff. Okay, so it's very simple to set up the data frame and the mask data frame, the true false data frame, and our DFB is looking sweet here. Okay, all right. Now let's look at our next item. So let's draw a separator here. And this time it could be an equal sign. Okay, so what about list of, what about series? So we can similarly do the same here. We will select the second from DF. Remember, DF is a 7 by, what is it? 7 by 10. data frame, and we'll select the B column. So SS is going to be a series, and we're going to explicitly construct a series and then tick off vertically, right? So 1, 2, 3, 4, 5, 6, 7. The vertical is kind of typed out horizontally. So that's why I say series, you should not think about it as a row vector or column vector. Think about it as a snake, so it will prevent you from locking it into a shape. Because when we selected DFB, it's actually a column to us. We'll think of it that way. But when we construct a similar series, there is no dimension. There's only how many data is in the item. So we're going to get as many as many cells in the series as we list the data here, 7. Then for the series, it's also subject to the same filtering selector mechanism. So SS select by SS true false. Okay, so SS true false is what we arbitrarily constructed, but SS is the derived data series, right? So we can see what is the outcome, and let's run it and see. Okay, so our df, first of all, our df dot b is this. We are selecting the second, 6, and the 6, the second and the second last, right? So this one and this one. And what did we get? This one and this one. Yes, exactly. Okay. And what else do we see here in this the SS2 here? The index labels are also copied. So we actually know that the so-called first data value is from index label 1 in the original series. So series also has a label. It's not exactly just a column vector. It also has a label. And that index label, remember, can also be ambiguous, can also be having noise, can also be undefined or something. So yeah, so keep in mind that, and then your life will be much better off when you use pandas, and all the ugliness that pandas occasionally kicks up, they're all because of the way it is being designed. So now that you have understood much better how various components come together, I hope you are able now to see much clearer why certain things are behaving the way they are. Okay. Okay, so let's just round up this part and get ready for the next video.